All right, welcome back everybody to Ask Why, and thank you so much for joining us. Over the last couple of weeks, we went on a journey. We called this the Capacitor Confession. We dove into the different technologies that we offer, from aluminum electrolytic to MLCCs, tantalum and film capacitors, and we kind of pulled back the curtains to show you guys what those products look underneath and what the best applications are for those products. Today, we have again with us Peter Blaze, Head of Technical Marketing, and I want to talk with him about taking us on a journey of a power supply. So, Peter, we talked about this earlier and you said, let's go on a journey. I'm an electron. How do I go in? I'm coming from the AC, I'm coming out of the plug. I'm going into a power supply. What capacitors should I encounter where?
Well, I think putting oneself as an electron and going through the circuit is really the best approach to look at this, because now we can look at the best technologies as we go through the circuit. So I'm an electron, I'm in the wall, in the plug, and I'm going into the power supply. The first stage I'm going to hit is the EMI front end. And for that, the capacitors that are going to be used are going to be X and Y polypropylene film safety caps. And hands down, that's the best technology that's out there. There is an option in the ceramics world for safety caps, both X and Y. They can be used typically in smaller, lower power systems, but for bigger power supplies, film, polypropylene, safety cap is going to be used.
Yeah, and you mentioned on the film capacitors for those areas, the reason we want to use them is because fire hazards, if failure occurs, and shock safety if failure occurs. So we don't want to kill anybody and cause a fire if something happens.
That's correct. That's correct, because when UL tests the parts, they don't look at it from an electrical perspective. They look at it from a human safety perspective. They don't want people to get burned up from a fire that's caused by parts failing, or they don't want people to get electrocuted. That's a critical function of that portion of the circuit.
So now that we cleaned up the EMI, what's the next stage?
So then we're going to go through the circuit. We're going to get rectified. And we're doing this from a simplistic perspective. So we're going to get rectified. And after we get rectified, we need to have a relatively stable DC voltage. And for that, we need bulk capacitance. We're rectifying a low frequency. So that tells me we need a lot of capacitance. It's going to be relatively high voltage. We're going to use aluminum electrolytic. That is from a cost perspective and from a functional perspective, the best technology to use there. And so aluminum electrolytic, and there's different form factors of aluminum electrolytics that you can use depending on what the form factor of the system, but technology there, aluminum electrolytic.
And you do mention that when in that area, reverse polarity is a very important issue to consider in those applications, because otherwise you create a smoke bomb. So we want to make sure that we install the capacitors the right way and don't expose them to any reverse polarity. So
absolutely, they must be inserted correctly and not backwards, because inserting backwards may take a minute or two, and then you're going to see poof, really bad experience. So from there, we're going to go and typically go into there'll be power factor correction section of the circuit where there could be some snubbers used, typically ceramics, C0G ceramics that would be used there. Maybe some films as well, that would be polypropylene films. This is really to make sure that the power factor correction, you want the load to look like a resistive load, not inductive load or a capacitive load, so you balance it out. After that, we're going to go into typically a resonance section where we've got a capacitor bank along with, say, a transformer. That section typically is going to be comprised of one of two technologies, either C0G ceramics or polypropylene film, typically pulse type rated polypropylene film for the resonant section. And that's really going to be frequency dependent. Rule of thumb there generally is 100 kilohertz. If you're below 100 kilohertz, generally the best technology from a cost perspective and a size perspective is going to be polypropylene film. If you go above 100 kilohertz or you're at 100 kilohertz, generally speaking, C0G or class 1 ceramics are going to be the best. There's some other variations of class 1s as well you can use.
And of course, when you talk about the ceramic capacitor in that application, typically you would have a bank of capacitors. It would not just be a single one.
Oh,
So
absolutely. It's going to be a matrix typically, and it depends on what the voltage is, whether it's a 1 by say 8 or 1 by 9 matrix, or a 4 by 9 or 4 by 8 or 4 by 5. It's depending on the voltage, and it's also depending on the current. And again, we have a tool that we're just getting ready to release. It's called the Power Array Calculator, that helps you choose what that configuration is based on the constraints of your system that you're putting together. From there, we're going to go to the output stage, and here you've got, it really depends on what the output voltage is. If it's a high voltage battery, such as say a electric vehicle, in that situation, you're typically going to use bulk polypropylene film caps as your output filter cap, in combination with some Caesar or G caps that handle the high frequency, maybe some X7R, but most customers actually using Caesar or G in that area. Or you're going to use, say, aluminum electrolytic. And the electrolytic that is going to be used probably is going to be hybrid or polymer technology if it's lower voltage. The reason there is that stage prior to that is going to be switching at a relatively high frequency, and your hybrid or polymer technology handles it much better than, say, pure aluminum electrolytic.
We talked about now coming in from AC to DC charging a high voltage battery, but of course there's going to be some control circuitry involved. So what if we are that electron and now we go into a lower voltage area, control circuitry and those types of areas? How does that look like? I'm going from a 12 volt DC rail to my rest of the system.
So absolutely. So let's talk about it, the embedded system. So the embedded system, which is controlling this, or if this power supply is actually going to power a low voltage system, such as say a computer. So in that stage, we're going to step down to different voltage rails. We're going to go from, say, I don't know, we may start out at 48 volts and go to 12, and then 12 to, I don't know, the logic level voltages down to 0.8 volts. In these areas, what we're going to do is we're going to use different technologies at different stages. So let's look at say the 48 volt. 48 volt, typically, that's the input stage where you need to decouple that system from the higher upstream. And so therefore we're going to use bulk cap, typically ceramic, class 2 ceramics, X7R. And then we're also going to use bulk cap. And typically, depends on the type of system, but generally speaking, we're going to use aluminum electrolytic or aluminum polymer, aluminum hybrid technology. Again, your higher performance systems would tend to use the polymer hybrid systems. Lower end type systems, just regular aluminum electrolytics, typically in the little tiny can surface mount V chips. From that stage, we're going to go to the 12 volt stage. That conversion, there's different topologies, but one of the dominant technologies today is some type of switch tank type architecture. Google came out with the STC architecture a number of years ago, and there's a number of iterations of that. That's a resonant topology type circuit. And in the capacitor stage of that, typically two technologies are used. It depends on the implementation of it. You've got a class, if it's a nice resonant type circuitry, you're going to use a class 1 ceramic, typically U2J, which gives you a little bit better dielectric constant than Caesar or G. There are some other variations that actually can go and utilize some class 2 ceramics because they're always in the positive stage. From there, on the 12 volt rail, you're going to use bulk cap, typically, again, combination ceramics, class 2 ceramics, as well as bulk cap, which is going to be tantalum polymer. That would be the dominant technology used there. Typically, tantalum polymer is used because, again, form factor constraint. They're putting these parts on the bottom side of the board. You don't have the Z-axis that can accommodate the big aluminum electrolytic cans down there. Do that for design densification. And then from there, we're going to go to the digital rails, say down to 0.8 volts. And we're going to go and use a combination of, again, ceramics and polymer technology. Polymer technology here is really dominated by two types of technologies. You've got aluminum polymer H chips, which actually look like the tantalum polymers, but inside they're aluminum elements, a different type of construction we talked about earlier. But these are surface mount low profile chips. Or you can use the tantalum polymer as well, and both are used in that type of application.
So I think when we started looking at the power supply, and we went through this journey of from an electron coming out of the AC line all the way down to logic level DCs, we can see that the technologies used in those types of applications are really all over the place. We go from film capacitor to aluminum capacitor to ceramic, back to different types of aluminum polymers, film capacitors along the way. And lower voltage levels, we then have also tantalums and more MLCCs. So as you can see, the technology really depends on the area that you want to use it in. So all of these different technologies can actually be utilized in your application. And Peter, I want to thank you for taking us on this journey this week for our Capacitor Confessions, and really breaking it down in a very simplified way to help our viewers and everybody else that's watching our podcast to understand exactly what technology goes where. So thank you so much for the series, and this will be the end of this particular series. And we have more coming out with our Ask Why podcast, and we do want to encourage you to keep on watching and keep on asking why.
Thank you, Simon. It's been my pleasure. Thank you.